بسم الله الرحمن الرحيم. بنرحب فيكم في lecture number 2. ما زلنا نتكلم عن optimization problem. This is the optimization problem part 2. اليوم بدنا نكمل، فرح نتكلم عن ال constraints واللي المحددات in many optimization problems. The variables are interrelated by physical laws like conservation of mass or energy, or by Kirchhoff's law, Kirchhoff voltage or current laws, and other system equalities. So these equalities must be satisfied. These equalities must be satisfied. Symbolically, we will represent this by a sub I of x. This is an equality, should equal to 0. This is for x as a vector belongs to the nth Euclidean space, where I equals 1 to up to p. So we have p number of equalities. A1 up to AP should equal to 0. These equalities must be satisfied before the problem can be considered, or before the problem can be considered solved. Okay. In other optimization problems, a collection of inequalities must be imposed on the variables or parameters to ensure physical realizability. And here we have C sub j of x greater than or equals 0 for x belongs to the nth Euclidean space, where j equals 1 to up to q. Must be satisfied before the optimization problem can be considered solved. Okay. Okay. So we have a set of equalities and a set of inequalities. The optimization problem which entail a set of equality constraints and possibly a set of inequality constraints is said to be a constraint optimization problem. So this is the definition of the constraint optimization problem. It's an optimization problem that contains equality constraints and possibly a set of inequality constraints. Okay. So the most general constraint optimization problem can be expressed mathematically as minimize f of x for x belongs to the nth Euclidean space subject to ai of x equals 0 for I equals 1 to up to p, and Cj of x greater than or equals 0 for j equals 1 to up to Q. Okay, so this is the most general constraint optimization problem. Minimize the performance index or the cost function where x is a vector belongs to the nth Euclidean space subject to ai of x. This is the set of equality constraints from I equals 1 to p, and another set of inequalities from j equals 1 to q. Okay. Let's continue with constraints a little bit. A problem that does not entail any equality or inequality constraints is said to be an unconstrained optimization problem. Again, this is the definition of the unconstrained optimization problem. It's the problem that does not entail any equality or inequality constraints. Okay, another point. Constrained optimization is usually much more difficult than unconstrained optimization. Okay. Constrained optimization is reformulated as unconstrained optimization unconstrained optimization. This can be done by redefining the objective function such that the constraints are simultaneously satisfied such that the constraints are simultaneously satisfied when the objective function is minimized. Usually the constraints are added in somehow in a certain method to the objective function, and everything is solved at the same time. So they are solved simultaneously. We will see this in the future lectures. Okay. Let's define another item, which is called the feasible region. The feasible region. Okay. What do we mean by feasible? The feasible region. Okay. Any point x that satisfies both the equality as well as the inequality constraints is said to be a feasible point. Of the optimization problem. So we call it a feasible point. So any point in the Euclidean space, in the nth Euclidean space, x, that satisfies both equality and the inequality constraints, we call it a feasible point. The set of all points that satisfy the constraints constitutes the feasible domain, region of f of x. Okay? So the constraints define a subset of the Euclidean or the nth Euclidean space. Therefore, the feasible region can be defined as a set. Let me define it here. So we'll define the feasible region as R, and this R is all the points X such that ai of x equals 0 for I equals 1 to up to p, and ci of x greater than or equal 0 for cj for j equals 1 to up to q, where R is contained in the nth Euclidean space. So R is contained in the nth, so it's a set that is contained in the nth Euclidean space. Okay, another definition here is that the optimum point, we could call it x star, must be located in a visible region. And so the general optimization problem can be stated as minimize f of x for x belongs to R, where R is defined as defined above here. So this is my R actually. So minimize f of x, any point x not in R is said to be a non-visible point. Non-feasible point. Okay. Let's take an example. And see those definitions that we have in this session. Okay. So we have an example by using a graphical method, solve the following optimization problem. Minimize f of x equals to x1 squared plus x2 squared minus 4x1 plus 4, subject to c1 of x equals x1 minus 2x2 plus 6 greater than or equals 0, C2 of x equals to minus x1 squared plus x2 minus 1 greater than or equals 0, C3 of x equals to x1 is greater than or equals 0, and C4 of x is equal to x2 is greater than or equals 0. Okay, before we start the solution, just look at the problem. We have to minimize this function. So this is our objective function, and those are all inequalities. The Ci's from I equals, sorry, from the Cj's from j equals 1 to 4, and those are the inequalities. All of them must be satisfied. So this is a constrained optimization problem, and we have to start solving this problem here. Okay. The first thing that we will do is to try to look at the problem from a different point of view. So the objective function. So we'll start the solution, and we start with the objective function. Notice here that the problem is in the second Euclidean. It's n e to the power 2, which means that you have two variables, x1 and x2. So we can look at the two-dimensional contours of the objective functions. The contour can be done in the following manner. So the objective function here can be stated as x1 minus 2 squared, x1 minus 4, x1 plus 4 can be put in this way, plus x2 squared is equal to f of x. And these are the contours. So the contours of f of x in the x1, x2 plane are concentric circles with radius equals to the square root of f of x, centered at x1 equals 2 and x2 equals 0. So this is the first, the objective function. It is contours of the objective function. They are circles. Concentric circles means that they have exactly the same center. The center is x1 equals 2 and x2 equals to 0. And we can just, if we draw the two-dimensional plane with x1 and x2 as contours, and we draw the contours of f of x. The contours, actually, they are the topology graphs in x1 and x2, and they draw the lines where we have exactly the same f of x. For one f of x, we have a line. So those are topological graphs. The center here is x1 and x2. So, sorry, x1 and x2, x1 equals 0 and x2, x1 equals 2 and x2 equals 0. So if this is 1 and this is 2, so these are the centers of those values. And we can draw circles for f of x. And we can continue doing the circles. So This one will be for f of x for certain value of f(x), another value for f of x, the square root of f of x, or the radius. So the radius is the square root of f of x. Okay, so those are the contours of the objective, our objective function. Okay, let's take the other inequalities and take care of them. Constraints. So constraints C1 of x and C2 of x dictates that x2 is less than 1/2 x1 plus 3, and x2 is greater than x1 squared plus 1, respectively. We mean respectively that this is for C1 of x and this one for C2 of x. Okay, so those two constraints, the first one is a line. So C1 of x is a line that will, when x1 is equal to 0, x2 is equal to 3. So this is 1, 2, and 3. And we have a slope of 0.5. So this one will be like this. So this is a line. Let me draw it with another. So let me draw it with the red marker. So this is C1 of x. Okay, C1 of x, and this is 3. Okay. C2 of x is a or it's a polynomial, second order polynomial, quadratic curve. When x1 is equal to 0, x2 is equal to 1. So this is the curve. So this one is our C2 of x. So we draw C1 of x, we draw C2 of x for the others. Okay. The constraints, while the constraints C3 of x and C4 of x dictates that x1 and x2 be positive. This means that we are looking for a solution to be in the first quadrant. So our solution will be in the first quadrant here. So this is, okay. Now, all those inequalities, the first one says that x2 is less than, so we have it below the red curve. The other one is x2 is greater than, so it means that this is our, so this shaded area is our potential solution, or our feasible region. So our feasible region is the shaded area that we have here. Okay, if we're trying to find the solution within our region, so the feasible solution is at a certain point where the slope of those eccentric circles have exactly the same slope as the green line from C2. So I will assume something here This is our solution A. Okay, so our solution is some circle topology or circle from square root of f of x, which will touch the C2 of x. So this is our A, and this is the feasible solution that, or our solution that we are looking for. So the feasible region for this problem is the shaded area. The solution is located at point A on the boundary constraints of C2 of x. So C2. So it's on the boundary constraints of C2 of x. Okay, if just in case, if we don't have those boundaries or those constraints, in the absence of constraints, the minimum of f of x, would yield point B as a solution. And guess where this point B to be? It will be here, at the center of the concentric circles of f of x. So if B is the center, this means that x1 equals 2 and x2 equals 0. So f of x will be 2 minus 2 is equal to 0, 0 squared plus 0 squared, and f of x is equal to 0. And so is the solution, and f of this x, which is equals to 2 and 0, is equal to 0. Okay, thank you very much. With this, we end up with definitions of the optimization problem, unconstrained and constrained optimization problem, and we'll see you in next lecture. Thank you very much.